Hello guys, today we're going to do the derivations for kinetic and potential energy. We're going to start with kinetic energy, and as you can see we have a model right here. We have a flat frictionless surface with a ball of mass m and velocity v, which will start at 0 as the ball is going to be at rest. We're then going to apply a force to the object, transferring energy from our body as we're pushing it into the ball in the form of kinetic energy. As we know due to the work-energy theorem, kinetic energy is simply the work done to this object. And as this distance is represented by d, we can say that, let's just aside real quick, the change in kinetic energy is equal to the work done, which in other words is the force applied to the object times the distance, which is represented by d, or the change in d, which is just however far the ball goes from its initial state to its final state. So for this derivation, we're simply going to expand that force one more time to get delta Ke equals mass times acceleration times the change in the distance. So we have this part of the derivation done. It's time to move on to the kinematics equation of v squared equals the initial velocity squared plus 2a delta d. Basic formula right here. And the goal of this part of the derivation is to find a value for a delta d, so which we can plug it back in to that kinetic energy equation. So to acquire that, first thing we're going to do is subtract the initial velocity squared from both sides, and once this is done, simply divide both sides by 2, giving us a times delta d is equal to v squared minus vi squared all over 2. Now we're going to take that expression and plug it back into that kinetic energy formula, combining the two, and we're going to get delta Ke equals m times v squared minus vi squared all over 2. Now we're just going to multiply those two parts, and we're going to get delta Ke equals 1/2 mv squared minus 1/2 mvi squared. Now, as we can see, it's only taking the initial velocity, which in these scenarios we're going to assume to be at rest, because kinetic energy starts from the time that there is any amount of motion. So instead of trying to find the change in kinetic energy, we'll find the total kinetic energy. And therefore, we can remove the initial velocity, and assuming that that is at 0, you would cancel out that part of the equation, giving us the infamous equation Ke equals 1/2 mv squared. There we have it. Now, moving on to potential energy. In this scenario, we'll have a very similar model, where we have a 180-degree bar, and we're going to drop a ball of mass m and velocity v, assuming v is at rest to start, and we're going to drop it into a free fall environment. Of course, here we're assuming that air resistance is non-existent, just to really show the concepts at work here. So as the ball goes down, the gravity, which is going to the acceleration at this point, is going to pull it down, and we're also going to record the distance the ball takes as h, the height. So we're starting off with a very similar direction as those kinetic energy derivations. So we're going to set the potential energy, or the change in potential energy, equal to W. We're going to expand it out, just as we did the last one, and then expand it yet again. So right here we also have identical formulas. And here it becomes a bit easier. As we know, the acceleration this ball is experiencing is entirely due to gravity, as there's no air resistance, there are no other forces to start at rest, and delta d is simply h, the change in height. Now, another thing we know is for the same reason that we're not trying to find the change in kinetic energy, we're also trying to find the change in potential energy. So here, instead of trying to find the change in the height, we can simply find the height. So we're just going to expand it, just like it shows there, expand it one more time. We can now see that the potential energy is equal to mass times gravity times height. There you have it. There you have those two derivations for potential energy and kinetic energy. Hope you enjoyed the video. Hope you have a newfound interest in physics. Like and subscribe, and have a great day.